Welcome to the SETI Colloquium series. Today we have Chris Burke, who's both at Ames and SETI, talking about Kepler. Chris was a graduate student at Ohio State University working on a transit survey of an open cluster. After that, he continued with transit work. He was involved with EXO survey at Space Telescope Science Institute and MERT survey at Harvard-Smithsonian Center for Astrophysics, and for the last 4 years has been around here working on Kepler. And today he'll tell us about the terrestrial planet occurrence for the Kepler GK dwarf sample. Chris?
Well, thank you very much. As we talked about, I've been doing planet surveys, searching for extrasolar planets for almost a decade now, and that's sort of the length of time that we found the first extrasolar planet discoveries. And so it's wonderful to have seen this whole huge population of planets that have been found with radial velocities, ground-based surveys for looking at transits as well, and then Kepler came along. And we also have microlensing and then now direct imaging ways of finding extrasolar planets. So this field has really just taken off. And so what I'm going to talk about is sort of narrowly focused on what Kepler has been doing. And specifically, I'm going to talk about, from all the Kepler discoveries, how many and what kinds of planets exist in our galaxy, at least in the regions probed by Kepler. I'm not able to do all this work by myself, so I have a huge list of collaborators here. Most of these people are on the Kepler project, a few external people. A lot of these are SETI employees as well. So a lot of these people work at NASA Ames and SETI. And a few of these people are going to be giving talks along the coming weeks. And so I encourage you, especially last week we heard from Tom Barkley talking about the follow-up mission of K2, but also finding extrasolar planets. So I would encourage people to also check out his talk from the SETI talk last week as well to get you up to date with Kepler and things. So just to quickly remind people of Kepler, it was a mission launched by NASA, and the prime mission was expected to last 3.5 years, and we met that prime mission, and we extended a little bit to get 4 years. And then several of our reaction wheels failed to end the prime mission, and so that's the data set that I'm going to be talking about today. So Kepler was taking science for almost exactly 4 years of continuous photometry of one patch of stars in the sky. The patch of the field we looked at is basically located towards the Cygnus constellation, and you can see our little grid of detectors. So we stared at this one spot for 4 years. So this is an unprecedented astronomical data set, specifically targeting extrasolar planets to find them, but also doing other kinds of awesome science like astroseismology and other things you can do with this data set. So over the 4 years, we gathered data for around 175,000 stars and searching for transiting planets. Now, the transit technique is kind of special. We sort of have to wait a long time and stare at these stars. And if we get lucky, one of these stars will have a little planet, and it'll happen to be crossed right in front of the star, causing a dimming of the flux. And this is really what we measure with Kepler. We take our digital camera and we measure the brightness of these 175,000 stars. And once every while, we'll see one of these little dimmings. And as you wait, then the planet crosses the star and goes back to not being blocking light from the star. And that little dip is how we tell that there's a planet around it. Now, we usually wait several times to see this signal repeat itself, and that's how we build confidence that there is, in fact, a planet and not just some spot or other phenomenon causing these dimmings. So these ultra-precise measurements are needed to find these planets. To give you an idea of this, a Jupiter, so a really rather large planet in front of the sun, causes a dip of around 1%. But what Kepler was really going for was these Earth-sized planets the same size of Earth that we live on here. And that's a much smaller signal than for the Jupiter planets. It's around 2 orders of magnitude lower, or about 0.1%. So that sort of drives you to space. You need to stare at these stars for many years at this very high precision and cadence to catch these transits. So then here are a lot of these discoveries. So this is summarizing the discoveries that have just come out with this newest analysis using what we call Kepler quarters, or basically a quarter of a year. So in this analysis led by Fergal Mullally, who's in the back row there, another Kepler project member, we've announced all of these Kepler planet candidates. And so this is a huge treasure trove of information to understand what kind of planets exist in our galaxy. Now, one thing you'll notice here in this plot is orbital period on the x-axis and planet radius on the y-axis. So you'll notice there's sort of a region here in the lower right corner where I'm sort of putting the cursor for those of you online as well, is there's a devoid of planets there. Is that meaning there's no planets that exist there, or is that due to our inability to find them? So remember, those are planets on very long orbital periods. It takes a year or longer for them to transit. And they're also very small signals as you go down towards the Earth regime. So these are the most difficult signals to detect. And we don't populate that region because of our limitations of our instrument and sensitivity. And so really what we're trying to do is understand how our instrument imprints on this diagram so we can back out what's the underlying planet population versus what's the planet population distribution formed because we can't find all these planets. And so one of the things you can do then is find these planets and make a histogram of them. And so here now is a histogram from those same figure, but now I've sort of put all the planets down in a histogram of planet radius. And so you can see several features here at large planet radii. Here on the right side of the x-axis, you can see the planet population increases up to around 2.5 Earth radii. That's kind of like a mini Neptune sort of thing. And then as you go to smaller planets, we see fewer and fewer. So this is the observed population of planets without any corrections for planets that we've missed with our sensitivity. So is this fall off of planets at planets smaller than 2 Earth radii, is that intrinsic to the planets that exist in our galaxy, or is that due to the fact that we can't detect all of these with Kepler? And so that's really the whole basis of the analysis that I've been involved with, is does this population continue to rise towards small planets? Does it flatten out, or does it actually go down? To understand that question, you have to understand the sensitivity of our survey to these planets. So to do this game, you need 3 essential ingredients. You need to understand 3 items. You need to understand your stellar sample. You need to understand the planet sample. And you also need to understand the pipeline completeness. And so by pipeline completeness, I mean these sensitivity effects, the fact that we're not sensitive to the smallest planets on the longest orbital periods. Now you need to know all 3 of these things very precisely to be able to understand what the underlying planet occurrence is. Now in this talk, you could give a talk, an hour talk on each one of these points, but what I'm going to focus on is the work that I've been directly involved in is the pipeline completeness. If you wait a month, I think Fergal Mullally is going to talk about the Kepler planet sample and stuff, so there'll be future Kepler talks here at the SETI environment to learn about those other topics. And so I'm going to talk about the pipeline completeness and really understanding the systematics of how well do we understand our data and our instrument in backing out what the planet population is. So I'll just have one slide about the stellar sample. For people who really like stars and are not interested in planets, this is the only slide about stars. I apologize. But this is a whole field of astronomy. People get very excited talking about the Kepler stars and this wonderful things you can do with it. So our understanding of the Kepler targets comes from the Kepler input catalog, a lot of work by the Kepler Stellar Working Group led by Dan Huber. And this is just a diagram of the effective temperature log G. So we have our mainly dwarf star sequence, M dwarfs down here at the cool edges leading up to our G and K population. Now in the blue or gray there, I've highlighted the G and K dwarfs that I focus our analysis on. And then you have all these wonderful giants and subgiants. Those are more difficult to find planets around, so we focus on just the G and K dwarfs. Overall, we select these GK dwarfs. We end up with around 91,000 500 targets observed by Kepler for a very long time. Now, our planet sample I just talked about, again, Fergal Mali is going to give a talk about this, and you could give a whole talk about this, so this is the only slide talking about the planet sample. But again, we saw this, and now I've culled the sample down to the planets found around these GK dwarfs. So there's still tons of planets to work here, even around that limited Kepler sample. Now, I'm going to focus on the analysis on actually a very narrow region here. Outlined here. I'm going to focus on this region of 50 days at the left side to 300 days. This is a nice parameter space, and talking about terrestrial planets, things with radii of 0.75 or larger up to 2.5 Earth radii. These are really kind of the super Earths, mini Neptunes, Earth analog things that could potentially be rocky that we're really interested in following up. So all we're going to do is talk about this region. And the reason why we're going to do that is because things happen when you go towards longer orbital periods. You go to lower SNR planets. These are things that have more difficult to detect and more difficult to make a reliable diagnosis of the signals that we see, and you have fewer transits to work with out there. So that's why I'm avoiding, currently in this first paper that I studied, short word of 300 days. Also, going down to shorter orbital periods, you run into things more frequently called astrophysical contaminants. These are things like eclipsing binaries that can mimic a transit signal. Also, there's a lot more planets down there. When we did this planet sample, we still had some manual vetting steps to select our planet sample. And so to avoid analyzing all of those signals, we looked at this narrow range. But what I do want to have as a side note, in the future, for Kepler, this is our last catalog that involves manual steps of deciding planet candidates. The catalogs we're working on now are completely automated. And so we can do over the whole parameter space an even selection of our planet candidates. So this is great for studying these things like occurrence rates, so you can really understand what kind of planets you're missing or throwing out. So so stay tuned for all the work that's going on in automating these planet samples. So I zoom in on that 50 to 300 day range, and in that range around these GK dwarfs, Kepler has found 156 planet candidates in that latest planet candidate catalog. So you can see then the general trend as you go down to long periods and small planets, the planet population falls off. And again, most of that is due to detection biases that we're going to try to work out. Just to state that we have a very low astrophysical false positive rate in this parameter space. It's around, we believe, only 4% of these dots shown here are not real planets. Most of them, we have pretty high confidence that they are actual planets. So here I talk about pipeline completeness. And I'm not going to go into all of the details. Just know that this is really the key point that has been missing so far analyzing Kepler data. A lot of the work that I've been involved in is analyzing for a single star. You can go to the catalog of Kepler objects and ask, for this given data set, what's the probability that I could detect a planet of any particular period and radius. So you can see these contours then, again, the white region here is where we're very complete. We have high statistics. The pipeline works very well. There are large planets on short orbital periods that you see many, many times in the Kepler data. This is where we're 99% or better complete. So you go to longer orbital periods down at Earth, down at 365 days, which is around about here. For this target, we have around a 20% probability of finding such planets around this target. Now, this is the critical information that you need to figure out these detection biases. And right now, all of this information is publicly available, so anyone can go to an acronym is NEXI, it's the NASA Exoplanet Science Archive, which has all this information. So if you're interested in performing these kinds of experiments with Kepler data, you can go there and say, I'm interested in these stars, and you can gather the data and make one of these maps for any target or any set of targets. So we've put a lot of effort to this, and this has really been a key missing component of a lot of previous analyses from Kepler data. So also just quickly point out, there's a lot of example code on GitHub. I put some code to be able to use all this data to ease the transition into doing this for researchers. So you can go there and play around with a lot of the Python code examples that I've put up. Again, it's to generate these detection contours for any particular Kepler target. So one target is not that interesting, so what you do is you combine all of these 91,000 detection contours. And so here then is the average detection efficiency from Kepler for these 91,000 GK dwarfs. Also, the points again are our planet candidates. So you can see our planet candidate sample falls off roughly kind of parallel to these lines of detection efficiency. So from here we can kind of see we're doing roughly modeling the correct observing degradation and biases as we go towards the small planets. Another good point is down here actually, after even 4 years of observing with Kepler at 300 days and 1 Earth radii, our average probability of detecting a truly Earth-sized thing is only 1%. That's the reality of the data we have. Now you go to slightly larger planets at these long orbital periods, and we're about the 50% recoverability at around a little above 2 Earth radii. So that's how you sort of read these diagrams. So you use this diagram then to correct the planet candidates that you've detected. So you have these three things, these three ingredients that you need. You need the stellar sample, you need to understand your planet sample, and now we have a complete model for the pipeline completeness. You combine all of these things then to correct your detection biases. In this model that I fit to the planet occurrence rates, it's a broken power law model. It's a parametric model that grows. We saw the earlier histogram of increasing planet occurrence rate, and then there could be a break at some radius. So we try to model these effects. And you use a lot of Bayesian MCMC parameter estimation things to do this, a modern analysis of this. So this then is the observed planets zoomed in on this, looking at the 2.5 Earth radii on smaller. We saw that decrease of the observed. This is without any corrections. And so then this is our model fit. So I was showing just the counts in the histogram. And now on the next figure, I'm showing the same thing, but instead of a histogram, I'm showing the counts in the points. And then the shaded contour is our model fit to this and our confidence region in that planet occurrence rates. And here again, I have not done any debiasing yet. So I'm just showing our model plus the planet population. So to get at the intrinsic population, then after you remove the detection biases of our survey, you can get at the intrinsic population. And so this is then the final intrinsic population that we can constrain after removing all of the Kepler detection biases. And we see the planet population is not falling off. That's just caused by our detection biases. It's actually slowly rising. So as you go towards smaller planets in this 50 to 300 day range, Kepler data is modeling an increase in the occurrence rate. There's more Earth-sized planets in this range than there are mini Neptunes or super Earths here at 2 to 2.5. Now, previous work has also found a break in the power law. We do not see a significant evidence for this break in this 2.5 to 0.75 range. Maybe there's a little bit of a break here, but it's not statistically significant yet. We do, however, at longer orbital, at larger planets, do see a break at 3.3 Earth radii. A little bit later figure will show that. But from this analysis with this new pipeline completeness from Kepler, we see just sort of a slowly increasing planet occurrence rate towards these terrestrial planets. Now, the next thing that I did in this analysis was I talked about the three ingredients, the stars, the planets, and the pipeline completeness. But each of those components has its own systematic effects. And this has been relatively ignored in the literature so far. So in this paper that I'm talking about that came out a couple months ago, we underwent a very substantial sensitivity analysis. So what we did is we changed one input assumption and then reran the entire analysis and see how that impacts your results. So we're really tracing out for different potential systematics in our ingredients, what is the impact of them on our planet occurrence rate statistics. And so what I showed earlier was just sort of our baseline, our best set of input ingredients. And now what I'm doing is showing an occurrence rate over from 1 to 2 Earth radii and 50 to 200 days. What's the overall occurrence rate in that box? That's sort of this orange histogram. So in that region, our best set of ingredients gives us an occurrence rate of around 33%, with a particular scatter shown by the orange histogram in that result. Now you see I have a bunch of other curves on here. This is doing the same analysis, but I only change one input ingredient. So for instance, one thing is the baseline analysis assumes all of the orbits are circular, but we know planets are not all circular orbits. They can have eccentric orbits. And so what we did is we assumed all of our planets, have an eccentricity of 0.4 and reran the entire analysis. And what that does is it shifts you over to this white line with the triangles. So that's kind of a modest 1 sigma effect, but it is an effect to take into account. And so there's a whole host of other things. Some of them are more important. So for instance, this white line with the circles that sort of gives you a much higher occurrence rate was where we sort of change our understanding of pipeline occurrence. So if we make our pipeline recoverability detection biases more pessimistic, sort of at a level where we think we can constrain them, but not quite, then that correspondingly gives you a much higher occurrence rate of around 55% of stars could have such planets of 1 to 2 Earth radii. And so the takeaway of this is there's been systematic effects that have been so far ignored. We've identified the most important ones, and we're working hard on the Kepler projects to reduce them. So currently the systematics are slightly larger than our statistical errors, but the good thing about systematics is most of them you can do something about. The statistical error bars we won't be able to do much about without launching another Kepler and getting more data, but the systematics we're working on to reduce. So there is hope, even though currently the systematics are dominating our error budget, that in the next year and a half that we have with the Kepler project, that we're working hard on these dominant terms. So I talked about analyzing this region of 50 to 300 days. And then you can ask, well, you have your planet population. What if you extrapolate that? There's a lot of interest for understanding habitable zones, especially habitable zones around stars like our sun, a G-dwarf habitable zone. One thing I did in this paper, the habitable zone is kind of a loose, fuzzy concept that is kind of difficult to convert our Kepler observations of period detections that we make in planet radius, and we don't really have great ideas of what the stars are like, into a habitable zone. There's so many different effects that determine the habitable zone. So what I did was sort of focus on a different area, is what I call affectionately Zeta 1.0, so Zeta Earth kind of, is the 1-year terrestrial planet rate. We can measure periods very well, so that's why I focus on just, if you look at 1-year orbital periods within 20% of Earth's orbital period and planet radius, what is the occurrence rate of such planets. This is kind of a subset of the habitable zone, but it's a much better, well-defined quantity that we can calculate from our Kepler data. So it's not quite what we want, but it's more directly relatable to the observations. And so then you take our solution for the 50 to 300 day range, extrapolate it to this Zeta Earth 1.0 region, and this is the overall occurrence rate that we find. So Again, the orange histogram is our best input ingredients. And now the x-axis is now on a log scale, so a log of -1 indicates that 10% of stars should have planets with orbital period and radius very similar to Earth, within 20%. So that's our current best estimate of this parameter space with Kepler data. Again, I have the other curves that show the systematics. Again, just like we showed before, changing one ingredient can change your result. And so when you include all these systematics, we have to include a more generous uncertainty on this zeta 1.0 parameter. And so in this log scale, values of 0.01 are not ruled out under all of these systematics that we currently have. So extrapolation to this region would suggest that we can constrain zeta 1 to 1% up to 0.3%. Now this is a large error bar, but before Kepler, this error bar would have been many orders of magnitude. We would have had no idea. It would all be just theories and conjecture. So this is a tremendous measurement that's been enabled by the Kepler science and the Kepler data. And there's still more to be done to understand these systematics. And we have a little bit better, right now we have a little bit more sensitive pipeline. So we're going to have our final pipeline run with Kepler project starting in September. And the planet population that will come out from that will start coming in next spring and summer. So we're very excited in this last run of our data that we have to really narrow these systematics down. So I want to shift a little bit of focus. I talked about the planet occurrence rates, understanding pipeline completeness. That's really what been my efforts on the Kepler project. Really enabling new science that we haven't been able to do before. All of this information is now in the public domain, so anyone can also do this original research. And another thing I've done is look at, we talked about GK dwarfs, but what about M dwarfs? What about the planets around K dwarfs or G dwarfs? Are there any trends in this planet occurrence rate with stellar effective temperature? Kepler does have some M dwarfs in its field. It's many fewer M dwarfs than we have G dwarf stars, just because they're so much intrinsically fainter. That's what drives that number. And so now what I'm showing here then is narrowing down to G dwarfs. We have about 73,000 G dwarfs with Kepler. And I'm looking at a period range of 20 to 50 days, so a little bit shorter orbital period range than we were looking at before. On the left then is our G dwarfs, and on the right we have around 3,300 M dwarfs. And then you can see the planet population. There's a lot fewer planets there in that diagram. Also, you'll notice the detection efficiency. These contours of detection are vastly different. M dwarfs are very small, so that the amount of light, amount of surface area an Earth will block is much larger for the M dwarfs. So we're able to detect smaller planets around M dwarfs. So if you want to understand these two planet populations, you have to take into account the fact that we have way fewer M dwarfs. Typically, for an M dwarf, we have better sensitivity than the G dwarfs. And so you need to take all this information into account. And that's really what you can do with the planet pipeline completeness work that we have. When you have it on a single target, then you can slice and dice your data into any stellar sample. So here is the difference between G dwarfs and M dwarfs. So then if you go and do the same analysis that I just presented for the G and M dwarfs, you actually get this very different occurrence rate. So each one of these curves then is this broken power law model for the intrinsic planet population. In yellow are the G dwarfs. So you can see in 20 to 50 days, if you start at larger planets, 4.5 Earth radii, you kind of see a characteristic kink or break there at 3 Earth radii. And then it kind of flattens off a little bit, but still is increasing as we go towards 1 Earth radii. Now that's the result for the G dwarfs. And you see something very different for the M dwarfs. You do see a modest increase, but the break occurs at a much smaller planet radius, around 2 Earth radii. The other thing you'll see is the occurrence rate is much higher. This is a log scale, so the occurrence rate for 2 Earth radii planets around M dwarfs is around 2% in these bins. and then it goes down to around 0.08% in that narrow parameter space for G dwarfs. So we have an order of 2 to 3 times more planets around M dwarfs than G dwarfs in this 20 to 50 day period range. Now this has been suggested by the earliest studies of Kepler. We had a lot of work by Andrew Howard and others sort of found this similar strong increase for planets around M dwarfs from the earliest Kepler data. This is from 20 to 50 days. Now with more data, we can go to longer orbital periods. Does this relation still hold? So if we look at longwards of 50, this summarizes what I just said. So G dwarfs likely have higher mini-Neptune occurrence rates than F dwarfs, but the M dwarfs has a significantly higher super-Earths. This has been suggested by earlier work shown here, but really brought into a sharp focus with Kepler data and the quantity that we have now. And so what if we go to longer orbital periods? So now we see something slightly different. Now I'm doing the same analysis, but 50 to 150 days. So if you just go a little bit factor of 3 in orbital period, now the situation is slightly different. The M dwarf population is relative to G dwarfs is decreasing as we go towards longer orbital periods. You no longer see a sharp break at 2 Earth radii. You no longer see this plateauing. But the M dwarf population is actually falling off rather quickly. The G dwarf population is very consistent with just a logarithmic distribution with period from that earlier bin, but the M dwarfs are falling off faster. So then you go to an even longer orbital period, 150 to 300 days. Now the problem is, with Kepler, we have yet to identify an M dwarf with a terrestrial-sized planet with a period longer than 150 days. So the M dwarf planet population has completely fallen off the map. Now this is not a huge statistical result. If you take the result from the previous bin, 50 to 150 days, and extrapolate that out, it's only sort of a 2 sigma discrepancy from extrapolation. But it is very, very intriguing that we see this general falling off in the population of planets around M dwarfs. So this really suggests to me that planets around M dwarfs may have, even though they're more numerous at the shorter orbital periods, they could have a completely different planet formation process than what we have with G dwarfs. And so I don't think people have really appreciated this before. We haven't had the measurements to really understand this. So I think there's a lot of great planet formation studies that can be done here. So I'm going to summarize the Kepler part. I have another little bit I want to talk about K2, the follow-on mission, that's more relevant to SETI, but I'm going to summarize this part really. We have these great new occurrence rate data products enabling new science that are all publicly available. We really want people to start using these in their scientific studies. And if you need help with them, please do contact us. We can help out with that. For the GK dwarfs, we see in this 50 to 300 day range and from 0.75 all the way up to 2.5 Earth radii, an occurrence rate of 77%. So what that means is the average number of planets per star is around 80% for GK dwarfs, just in the 50 to 300 day range. Again, the systematic errors are dominating this. So the uncertainty has a large range at this point, down to 30% and all the way up to maybe 2. You can dynamically pack many, many terrestrial-sized planets in this 50 to 300 day range. That's not, this upper limit of 2 is not ruled out from dynamical studies. We don't see a break in the planet. Previous people have sort of hinted at a break in the Earth-sized planets between around 2 Earth radii. We don't see that for the G dwarfs. We see it at a much larger radius than what has been previously indicated. Also, going at this M dwarfs versus G dwarfs, we see a very different population of planets around M dwarfs than we see around G dwarfs. The planets around M dwarfs are really dropping off very quickly beyond 50 days. So I'm giving a talk here at SETI, And so I wanted to take the opportunity to give just a little 5 minutes about the follow-up mission to Kepler. And there'll be time, and just to warn people, there'll be time for questions about the Kepler stuff that I just talked about after, at the end of the talk here. So hold your questions for that part for right now, and we'll just get through this K2 stuff. So K2 is, after the reaction wheels of Kepler failed, K2 was a reinvented, the spacecraft was reinvented into a new mission to look at the, given its constraints of its reaction wheels, it could look at the ecliptic. And so Tom Barkley gave a talk about the K2 opportunity last week here. And so I'll sort of presume people know a little bit about it, just to keep this part short. And basically Kepler K2 now is using this Kepler spacecraft to look at several fields along the ecliptic around 80 days each. So instead of Kepler, which stared at one field for 4 years, K2 is looking at separate fields for around 80 days and then moving on. So this ecliptic region is actually kind of interesting for some SETI science here. And so I've been proposing targets for the K2 mission of stars, our stellar neighbors closest to us, that are in this ecliptic region. And the reason why this is interesting for SETI science is because all of these stars that are well aligned with the Earth's ecliptic can also see us, the Earth, transiting the sun. So if you were to go to a star and you had your own Kepler telescope on some star out there and looking at the sun from a distant place, and you had the proper alignment to be, and you were along the ecliptic, you would see the sun, the Earth, transit the sun every year. And so it is feasible for another civilization out there that has a Kepler, has discovered Earth before in the past. I'm going to ask you to hold the question until the very end. Thank you, though. So this is not a new idea. Many of you in this room have actually been proposing these ideas to focus SETI surveys at these targets for many years now. So basically, stars passing within 0.26 degrees of the ecliptic currently can see the Earth transiting the sun. And so there's a lot of worry about, should we be communicating with Earth or with external civilizations? The reality is we already are. To these stars within 0.26 degrees of the ecliptic, they're seeing us transit. Not only are they seeing us transit, they're seeing our photons if they have really awesome direct imaging instruments. They're seeing our gravitational influence if they have really nice radial velocity measurements. So a lot of information about the Earth's existence are already flooding out at the speed of light for billions of years, not just modern civilization, but billions of years that the Earth has been orbiting the sun. So currently, how many extrasolar planets have this precise ecliptic alignment? There's only 2 extrasolar planets known, a transiting hot Jupiter, WASP-47, and then also a directly imaged very young planet. I won't try to pronounce that name. So this picture of the sun here is actually, if you were to go, if there are whatever at WASP-47 and they're looking back at the sun, this is about the inclination that Earth would be transiting our sun from the perspective of anyone at WASP-47 performing a Kepler experiment. I actually simulated that, so I grabbed one of our Kepler targets that would have the right apparent brightness if you were located at WASP-47. And here is a detection of the Earth from WASP-47 if they have a Kepler. This is one of our better Kepler targets with very low precision, but it is possible to detect Earth, the Earth from WASP-47 if they had their own Kepler. So I have this, so I've been proposing to K2 that what I call the K2 Exoplanet Ecliptic Survey, or KEYS is affectionately acronym. And so the goal is to really significantly expand the number of known ecliptically aligned exoplanets for current and future SETI searches. This just shows the kinds of planets we can find with K2 sensitivities. The red points are transiting planets that have been found from the ground. Blue points are the expected sensitivity of the kinds of planets that K2 will be able to find. So we'll really be able to find down in these mini Neptune super Earths, and if we're lucky, some Earth-sized things that are ecliptically aligned with K2. So a whole different regime of planets can be found enabled with K2. Why are we interested in this? Well, from a SETI standpoint, we both see each other transit. Now, this does have some advantages for the symmetry of us, both the systems transiting. One thing is, it's hard to measure radii. The transit technique is one of the few techniques with modest observational capabilities to get a nearly direct measurement of the Earth to very high precision. A lot of people say, well, anyone in the future with direct imaging can detect Earth, but you won't be measuring the radius of the Earth. You have to extrapolate. I don't care how precise of a spectrum of the Earth you can take from direct imaging. You always have to model the atmosphere. You have to understand the albedo. You won't get a very good constraint on the planet radius. So you may not be able to confirm the rocky nature of Earth if you're an external observer just from direct imaging. If you see us in transit, you can get a very direct measurement of the Earth's radius. That may suggest these systems on these ecliptic aligned orbits may be prioritizing communication with Earth. That is purely conjecture, but it does lead, gives you some arguments for why they may be trying to communicate with us. We may be able to see them since if their system of planets, we won't be able to find their habitable zone planets with K2, but if their systems are coplanar, we detect an inner planet. You can start monitoring these stars. You may be able to find a secondary eclipse to find evidence of non-thermal emission or blips or narrowband emissions. Again, these follow in with a lot of the SETI efforts. And so you'll have some targets maybe that are higher priority. Again, if this other system, it's transiting, if it's coplanar, interplanetary communication systems, or a recent paper by Gouchon and Loeb from Harvard, if you have a light sail propulsion system in the microwave to go between these planets, this light will be heading right towards us if those systems are coplanar. Again, then the artificial transiting structures. A lot of times there's energy arguments that artificial transiting structures may actually be energetically feasible to keep a signaling system going for a very long amount of time. So these are reasons why, just a few of the reasons why I think finding these mutually transiting systems is actually should be prioritized in SETI searches. And you all are the experts for that. I do not pretend to be an expert in SETI. You have probably many more lists of reasons for these as well. So I would talk to me. I'd like to learn about them as well. Finally, just the status of this. So on the left is just our detectors. And this ecliptic, the 0.26, is actually a very narrow region. So each of these squares is one of our detectors, and the gray band is this 0.26 degree from the ecliptic region that can currently see us transit. We actually survey a little bit wider region. And the reason why we do this up to a degree is because the Earth's inclination is not stable. There's forcing due to Jupiter. It sort of undergoes a Milankovitch type of variation, has a characteristic timescale of around 100,000 years. It's been modeled to have an amplitude of around 0.75 degrees that our inclination is varying. Also, with proper motion of the typical neighbor stars and the galactic orbit acceleration, we really don't expect stars, our stellar neighbors, to dwell in this ecliptic region for longer than 100,000 years. So that's why we sort of go to this a little bit higher 1 degree region rather than focusing on the 0.26 degree region. But so far, we have scheduled targets for around 3,000 targets with the KEYS project. We expect there to be around 2 planets for every 1,000 target dwarf stars that we observe with K2. So we may have the data available soon to find more of these. This data is getting to be currently publicly available. Anyone can analyze these light curves now. So if you're looking at these particular targets, you find something interesting, let me know, because I haven't had time to actually look at them in too much detail yet. So get out there and find these things. That's what I say. And so that's all I have to talk about. I'll stop there. Thank you. That's all I have.
Okay, the questions are on. Okay, let's start with this side.
There's something I need a clarification on, their probabilities. Is that just for stuff that we're looking at with the original Kepler data that is transiting, or have you made a correction for the fact that the planes are unlikely to match up?
Exactly, yes. So we correct for that inclination bias. So the numbers I quote are for taking out that bias.
Okay.
So 77% of targets, this number here, have planets on a uniform distribution of inclinations relative to Earth.
And so obviously the correction changes as the period changes.
Exactly.
Yeah,
You have to take all that into account. So
right.
inclination and SNR go into that detection model.
Chris, you used planetary radius and period as independent parameters. I noticed you didn't combine them into habitability. But if I were to ask you, what's the bottom line for GK and then for M dwarfs in terms of what fraction of stars have something that is roughly in the habitable zone, what would your answer to that be?
My answer to that is this figure here, specifically for GK dwarfs. And again, I personally feel there's too much uncertainty in the occurrence rates if we just deal with period than to worry about dealing with insolation flux and all the factors that go into habitability. So I've specifically kept this simple so that you can get a direct answer. So my simple direct answer is 10% of stars have a terrestrial planet within 20% of the period and radius of Earth. That is probably a lower limit to Eta Earth. So I would say a strong lower limit to Eta Earth is my lower limit on Zeta 1. Whoops. So a lower, so 10% is probably a lower limit to Eta Earth. But the specific question is very specifically answered here.
And for M dwarfs?
I haven't studied the M dwarfs in detail, but it's a similar type of thing if you do the same thing, maybe a little bit higher.
I have two questions. First of all, one problem with mutual observability is that they're not going to want to aim their Kepler telescope along their ecliptic until their reaction wheels burn out. And if the telescope's designed a little bit differently, that might not.
Yeah, all of those things are completely conjecture. We have no idea what, even if there's someone out there. But it is, I find the symmetry of, we have an instrument, we have the capability to do this, we have the capability to look out. This is currently available with Kepler. That's our first ability to find terrestrial planets at long orbital periods. We will have follow-on capabilities with direct imaging, microlensing in the future to also have capability of this. So I'm just trying to motivate that we can do this now, so what's not to say someone else is not doing the same to us? I don't know the answer to that better than anyone else in this room, but that really is what motivates me and excites me to understand these things.
And my other question is, if you find a larger planet transiting that's easily within the Kepler detection parameters, doesn't that make any marginal signal of a smaller planet more likely to be a transit rather than something else because of the fact that you've found their ecliptic plane and their...
If you have multiple planet systems, it is way more difficult to think of scenarios like eclipsing binaries that would have multiple detections. So a gentleman over here on the end there would tell you if you have at least 2 detections, it's highly likely that's a valid, a real planet, confirmed planet, and not a signal. Now, if you have a giant planet, we can't always sort of say, well, we're going to accept lower SNR signals. Maybe that was the. That was my question. Yeah, we don't typically do that with Kepler. We have a we're interested in a very uniform analysis. So we generally treat all of our stars the same, and we have a similar detection level for all of our targets. That's not to say that someone else cannot. This data is all publicly available, so anyone else is able to go in the systems where we know planets and relax their criteria and dig up maybe some more planets. I encourage people to do that. Kepler project has not focused on that right now.
Hi, Chris. Thanks for the nice talk, and I think you're doing a very good thing with focusing on zeta rather than eta sub Earth. But let me push Seth's question one step further. Could you please go back to the slide where you showed the rectangle definition of zeta?
Certainly.
So what you're saying is that in the light blue square, the occurrence is 10%. What is the ratio of the light blue square area to the dark blue square area?
If you want to adopt that blue area, I would say factor of 4.
Factor of 4. Okay, so then we get 40% in the blue square if you are comfortable with adopting that as your definition, of course. So, which is a big if, I realize, but
what I will say is my solutions in the 50 to 300 day range are available and all published. So you are welcome to extrapolate them to your heart's content to any region that you see best fits your science. And so I have given a very specific definition, and anyone's able to make it larger. I'll stick with my particular published result instead of extrapolating to larger regions. But you're able to do it if you want to spend the time to.
I have apparently a naive view with regard to the orbit and the masses, and I don't understand why all that hasn't been worked out in the past by Kepler and by Newton. It appears from your scattergrams here that given sizes can appear at different places with different masses of stars and different masses of planets, but why isn't that well understood?
The only planets we knew about as of this decade were our solar system planets. So the only ones we knew about were Jupiter, so we can measure Jupiter's mass and radius, Neptune, Uranus. There's actually nothing. There are no 3, 2, 1.5 Earth radii planets in our own solar system. So we didn't really know that they existed. There were a few detected before Kepler, but really Kepler just, as you can see in this figure, these planets look nothing like we have in our solar system. So we're just getting started of measuring the properties of these different kinds of planets. Kepler's laws apply to all of these planets that we've discovered around other stars. So we expect universal laws to apply to these other stars and planets. In general, Kepler is breaking new science ground of, are there planets like Earth? Are there planets like Jupiter? There are, but there's also other kind of planets that we have no idea what they're like right now. But we do expect them to follow the laws of physics in the order that apply to our solar system.
Chris, a question on this same chart. If I understood this chart correctly, I mean, if you're looking at the lower right-hand section of this quadrant, that's where we're at the limits of sensitivity or limits of capability of the instrumentation. If that's the case, isn't it a little bit dangerous to make conclusions about things like planet formation around M dwarfs if M dwarfs kind of represent the very edges of instrument sensitivity and capability?
Not for, if you do the statistics right, which I would claim I have done correctly, we have a lot of good statistics for planets, periods of 10 to 50 days. So that was the initial result that I showed with the way larger M dwarfs. That's a very solid result. That does not go away if you explore the systematics. As you go to longer orbital periods, it's pretty clear that M dwarfs are starting to come down. We still have good statistics there, I would argue. For longer orbital periods where I showed there was no M dwarfs, we would expect that result. That's only a 2 sigma result, that things have completely disappeared longwards of 150 days, I believe. So the statistics I've shown in this presentation, I believe, are done correctly. It is clear that the planet population is most definitely falling off for M dwarfs. Whether it continues to fall off beyond 150 days, that's only a 2 sigma result. We probably will not be able to improve upon that, unfortunately, with the Kepler data set.
Okay, over here. Yeah, this may be just a terminology issue. The sun is a G star, right?
Yes.
What's a G dwarf?
A G dwarf is a star like our sun that's not an evolved subgiant, that has not yet evolved to the subgiant or giant phase. So these are, so stars like our sun remain a dwarf size or constant size for 8 gigayears or so, and then they evolve very quickly to a non-dwarf G. Sometimes they, yeah. So it's just a main sequence G star like our sun. Good.
Okay.
Good question.
Next question. Has anyone else looked at the population of F stars or A stars, or I forget how to go backwards?
Yes, the F stars for Kepler, we do have a good sample of them. They are much larger stars, so we're not able to really find the Earths at long orbital periods around them. So you can find Earths at periods of like 10 days, 20 days around the F stars. Previous people have looked at the Kepler sample. I think some of those are biased because they haven't had this pipeline completeness model that I developed yet. But yes, people have looked at it. That's a work I'm working on as well with this new, very nice detection model that we have.
If you have further questions, you can come up to the speaker after the talk. Now we're going to thank our speaker again and present a special SETI mug. Everybody gets.
Oh, yeah.